Hello, everyone. I'm Georgia Koutrika, and together with George Katsogiannis, we are going to present deep learning techniques for text-to-SQL systems. But first, we need to ask ourselves why we need text-to-SQL systems. Nowadays, we generate many different types of datasets, and this data actually can be used by many different types of users. For example, scientists that are looking for insights, patterns, or information, or other types of users. Essentially, the benefit of data exploration becomes increasingly more prominent. However, the volume and the complexity of data makes it rather difficult for many people to query data, and database query interfaces are notoriously known for being not user-friendly. Essentially, it is very hard to write an SQL query when it would be much easier to say something in natural language. For example, here, the user just wants to ask which cities have a year-round average temperature above 50 degrees. Natural language interfaces or text-to-SQL systems are a holy grail for the database community for many years, since the 70s actually. So essentially, Ted Code was saying that we need to allow users to be able to use their native languages if we are to unlock the potential of data and databases. So here in this tutorial, we are going to describe what is a text-to-SQL problem, give an overview of the landscape. Then we are going to focus on two of the most prominent benchmarks that essentially enable the development of deep learning techniques for solving the text-to-SQL problem. We're going to see how natural language can be represented and given as input to such a system. We're going to see different categories of approaches, key text-to-SQL systems, and of course, we're going to conclude this tutorial discussing about challenges and research opportunities. Now, the text-to-SQL problem in principle is very simple. You have a query expressed as a natural language query. For example, which cities have a year-round average temperature above 50 degrees. The system can magically understand that this query is translated to this SQL query, quite complex query in this particular example, executes the query and generates the result for the user. Now, the text-to-SQL problem sounds easy, but in reality, it hides many different challenges. For example, from the natural language side, natural language is known to be ambiguous. For example, when we say, show information about Paris, do we mean the city? Do we mean the person? For example, what about references? How we link parts of the query to the schema? For example, when we say model, does this refer to the car model? Does this refer to the engine model? What about missing information? When we say the president before Obama, we refer to US presidents. How does the system understand this information? Other types of challenges like user mistakes, when you have spelling errors in the query, how does the system figure this out? Now, from the perspective of the SQL brings its own challenges in the equation. First of all, it comes with a very strict and grammar and limited expressivity. And that means essentially two challenges. The first challenge is that when we generate an SQL query, it has to be strictly syntactically correct, otherwise it will not be executable. While in the case of natural language, we can allow for various mistakes, but still the natural language sentence would be understood by a person. The other challenge here is that when we say something in natural language, it may be very simple to express it. For example, give me the actor that has the most movies, but the equivalent SQL query may be quite complex. And the other, of course, challenge comes from the database perspective. Now, the user data model may be totally different from the data schema, how the data is actually stored in the database. For example, when we say find actors who released the movie this year, this may be actually an SQL query that needs to join many different tables in order to bring together directors and movies. Now, early approaches essentially are following a system workflow that looks like this. Essentially, you have the query, that is given to the parser. The parser is responsible for decomposing the query and understanding the main parts of the query, terms, phrases, and so forth. Then the entity mapper is responsible for finding how these parts of the query actually map to database elements, values, relations, attributes, and so forth. Then you have the interpretation generator that essentially generates an intermediate representation of the query that is, however, understandable by the system. And then the SQL translator is responsible for generating the final SQL code that maps to this query, and it is executed over the database. Now, early systems of text-to-SQL systems are essentially falling into three categories. We have keyword systems that follow a search engine-like functionality, where essentially user queries are expressed with the help of keywords. And now here we distinguish three prominent early systems. Discover, which essentially introduced the idea of generating query interpretations as subgraphs over the database schema graph. Then we have Discover IR that introduced the idea of using information retrieval style ranking for a query disambiguation, and Spark that introduced fast execution methods. Then the next category of systems, like ExpressQ and Soda, essentially enable supporting more complex queries that have aggregate functions, group bys, comparisons, and so forth. Moreover, they impose a certain syntax in their input in order to be able to parse the user query. So, for example, if we wanted to ask for how many movies a certain actress has acted in ExpressQ, this would be in the form of count movies, actress Priyanka Chopra. Now, the last category is, of course, natural language systems such as NALIR and Athena. NALIR essentially is the first to introduce a syntactic parser to understand the full structure of the NL query. And Athena essentially introduced the concept, the use of ontologies to map the user data model to the actual data schema. Now, if we want to see how a query would flow through such a system, and in this particular case, we're going to use NALIR, let's take a look at this example here. So we have a query, what movies have the same director as Revolutionary Road? The parser will generate this syntactic tree that captures the parts of the query and how these parts are related to each other. Then the entity mapper comes in and maps query keywords to schema elements. For example, we see here that Revolutionary Road is actually a value of movie title. Then the interpretation generator takes these previous outputs and generates a new representation of the query that captures the database elements that participate in this query and how this should be processed in order to generate the desired result. And now it is very easy for the last part of the architecture, the SQL translator, to take this and generate the SQL code that will bring the desired results to the user. Now here, in the last few years, we see the dawn essentially of deep learning text-to-SQL methods. And that essentially, the main difference of these systems lies in the fact that now the text-to-SQL problem is mapped to a language translation problem. And these systems train over a very large body of NL to SQL pairs in order to be able to learn how to translate an NL query to an SQL query. Such systems essentially became possible due to the emergence of two very important benchmarks. The first one is WikiSQL, which is a crowdsourced dataset containing 18,000 NL and SQL pairs. The characteristic of this set is that the NL questions essentially are over tables that are gathered from Wikipedia. So essentially, we're not talking about entire databases, and that's why the SQL queries that we observe inside WikiSQL are rather simple ones. Another issue is that in WikiSQL, we see queries with many mistakes, and essentially research here suggests that we have already reached the upper possible bound for accuracy in WikiSQL. And let's see two examples, one good example and one bad example to get an idea of how these WikiSQL queries look like. For example, here we have a table from Wikipedia about players. The NL query says what nationality is a player marks the box, and we see the pairing SQL query. Now, a bad example essentially is this one here, where up here you can see the original Wikipedia table, but unfortunately this table was copied incorrectly in WikiSQL, which resulted to generating this SQL query, which doesn't make sense. And of course, the resulting NL query is even more incoherent. So this is an example of a pair of NL query and SQL that is not useful for either for training or for the evaluation of a system. And now we go to Spider. This is a different and quite a smaller set of queries compared to WikiSQL, around 10,000 questions. Over now 200 databases from 138 different domains. It is a set annotated by 11 Yale students. Queries are divided into 4 categories: easy, medium, hard, and extra hard. And we see all types of different SQL elements, joins, group bys, union, and so forth. Now, the characteristic of this dataset is essentially that it has more complex query and it is also of much better quality. Now, let's see an example of a query. Here we have a database of 3 tables. And the query is how many heads of the departments are older than 56. The corresponding SQL query is the one that we see here, which is quite simple, but we also have much more difficult, harder examples like this one here, where essentially the corresponding SQL query contains joins, group bys, having, and so forth.
So let's take a look now at how we can represent and how we can process natural language when we're working with neural networks. The main problem here is that neural networks can only accept numerical inputs, so we must find a way to transform our text inputs into numbers. The standard way that this was done until very recently was by using a word embedding algorithm, such as the more primitive one-hot embeddings, or a more advanced algorithm such as word2vec, glove, or wordpiece. And we would process these numerical vectors with a recurrent neural network such as an LSTM network. Recently, with the introduction of the transformer neural architecture, we have seen the rise of language models such as BERT, which is very frequently used in Text-to-SQL systems, but even more advanced and better optimized variations such as Roberta, or even specific language models for tasks that process tabular data and structured data such as TABERT and Grappa, which are very useful for the Text-to-SQL problem. So let's take a look at how glove embeddings work. The idea here is to create meaningful vector representations for words. And the way that this is achieved is by using an unsupervised learning method based on the co-occurrence of words in the training corpus. Some very interesting features of glove is that it creates linear substructures that represent word relations. So in this example, we can see that the words man and woman have similar substructures to the words king and queen. And it is also very easy to find semantical near neighbors. So for example, if we wanted to find neighbors of the word frog, we would get even very rare and specific or scientific words, such as the ones we see at the bottom right. And if we wanted to use glove embeddings, we could download a pre-trained vector set that is made available by Glove's creators. And it is usually created from a large corpus, such as Wikipedia or a crawl from the internet. So let's take a look at BERT now. BERT is essentially a very large pre-trained neural network. The base model has 110 million parameters, but there are even larger variations. And it can be applied on a very wide variety of natural language tasks by adding a few task-specific layers that process BERT's outputs. And in the paper that it was introduced, the authors showed that it can achieve state-of-the-art results in many natural language tasks. Now, the way BERT's architecture works is that it uses many transformer layers stacked on top of each other. It takes as input a sequence of token embeddings that are transformed using word-piece embeddings. And its output is a sequence of equal length to the input. BERT is pre-trained on a very large training corpus of almost 3.5 billion words. And it is trained simultaneously on two tasks. The first is the masked language modeling task, in which we mask out certain words of the input, and we ask BERT to predict which words are missing. And the second is the next sentence prediction task, in which we give two sentences and we ask BERT to predict whether the second sentence is the next sentence from the first. So here we can see an example input. We always start our inputs with a classification token whose output can be used for classification tasks. Then we have the first sentence with the word masked out. We mark the first sentences ending with a separating token. Then we have a second sentence with a word masked out as well, and a separating token to mark its ending. And here the model should predict the correct masked words, and it should also predict that the second sentence is in fact the next. So when we have a pre-trained model of BERT, we can then fine-tune it, which essentially means train it even further on the task that we want to solve by adding a few extra layers that can process BERT's outputs. And this essentially is an application of transfer learning. So here we must make two decisions. We must decide how to give our input to BERT. So let's say that we're using the WikiSQL dataset. We can say that instead of the first sentence, we will give our natural language question. And instead of the second sentence, we will give information about our table and its columns. And then we have to decide what to do with the output that BERT is going to give us. So for the WikiSQL task, we could decide that we're going to use the classification token to predict how many conditions we will have in the where clause, and so on. And we will see more about this example later on. So now let's take a look at three main categories that we can separate text-to-SQL systems based on their decoder's output. First of all, we have sequence-to-sequence approaches, which consider two sequences, the natural language question as the input sequence and the SQL query as the output sequence. And by doing so, the text-to-SQL task becomes a sequence-to-sequence transformation problem, simplifying the problem because the network essentially needs to learn how to generate a sequence of token that is the SQL query. So this approach simplifies the problem, but it leaves a lot of possibilities for errors because nothing prevents the system from producing syntactical errors when predicting outputs. And this is the reason why it is not used so often in recent works. Another approach that was created to tackle this drawback is sketch-based slot filling approaches, which consider a sketch of a query with missing parts, with slots that must be filled. And by doing so, we now have to only predict certain slots in the sketch and not the entire SQL query at once. And this approach simplifies the task, and it reduces the opportunity for mistakes by a lot. But at the same time, it is very hard to extend this approach to more complex queries because we always need a sketch to fill, and it is not that easy to design a sketch that can extend to more complex queries. So another approach that was proposed in order to achieve larger query expressivity and in order to capture more complex queries is the grammar-based approach. And systems that follow this kind of approach generate a sequence of rules instead of simple tokens. And when we apply these rules sequentially, we can produce an SQL query. And these kind of approaches make it easier to avoid errors because we designed our grammar in a way that it is not possible to generate syntactically or semantically incorrect queries. We can cover more complex SQL queries, but at the same time, these kind of approaches need more complex designs and more intricate approaches. So now that we have seen the three main approaches, let us take a look into some key text-to-SQL systems. We're going to see one sequence-to-sequence based system, three sketch-based systems, and two more complex grammar-based systems. So Text-to-SQL was the first neural text-to-SQL system to be proposed. It was proposed along with the WikiSQL dataset, and it works on the WikiSQL dataset. The way it works is that it transforms the input into vectors using glove embeddings. Then it processes these embeddings using LSTM encoders. And we have the same LSTM encoder for all three networks of Text-to-SQL. And Text-to-SQL uses three separate networks for predicting different parts of the SQL query. So it has a network that is going to predict which aggregation function will be present in the select clause, for example, count, max, average, and so on. A second network predicts which column of the table will appear in the where clause, in the select clause. And a third network is responsible for predicting the entire where clause. And this network follows a sequence-to-sequence architecture, and this is the main reason why Text-to-SQL is a sequence-to-sequence based system. And this is also the reason why it is very possible, and this is why Text-to-SQL can generate syntactically incorrect queries, because this third network is tasked with predicting the correct structure of the where clause and the correct SQL keywords. So for example, at prediction time, this network could forget to predict the where keyword, and this would obviously result in a query that will not be executable. SQLnet is a sketch-based system that was proposed to tackle this exact problem. It is completely sketch-based, and it achieves this by separating the network that predicts the where clause into four different networks that predict different parts of the where clause. So it has a network that predicts how many conditions will be in the where clause. A second network predicts which columns will be present in the where clause. A third condition that predicts which operators will be present in the conditions of the where clause. And the fourth network that predicts the value of each condition. Now, this fourth network is also a sequence-to-sequence network, but the important difference here is that it is only burdened with predicting the value, and it does not have to predict any SQL keywords, or it does not have to follow a specific syntax. So whatever prediction it makes, it might be incorrect, but we will have a query that is syntactically correct. We must note here that it is possible to generate semantically incorrect queries, and we will see about that later on. Another important feature of SQLnet is that each network uses its own LSTM encoder, which provides better accuracy compared to Seq2SQL, and it also introduces column attention, which essentially is a neural module present in all the networks of SQLnet that tries to find connections between the natural language query and the table's headers. Moving on, HydraNet is another sketch-based approach that works with the same sketch as SQLnet. Its main feature is that it relies completely on BERT. It only uses BERT and some simple linear networks that process BERT's output to make predictions. And we could say that it follows the way BERT was pre-trained, and it's a very natural implementation using BERT. Another very important feature of HydraNet is that it processes each column separately, in contrast to most approaches who give the network all the table columns at once. Now let's see more specifically how this is done. So we would construct an input, starting again with the CLS token. We would then add the natural language question. We would mark its ending with a separating token. And then for the column we are processing at the moment, we would add its type, integer, string, and so on. We would add the table's name, and we would add the column's name. And we would mark the end of the column information with a separating token again. We would then give this input to BERT, and we would get an output of equal length. And then we would use the classification token to perform some classification tasks, which essentially is predicting certain slots of the sketch. So we would predict if the column we're processing at the moment appears in the select clause using a very simple linear layer. We would predict which aggregation function should be used with this column, if this column appears in the where clause, and if it does, which operator should be used for this column in the where clause. And we would also make some predictions using the outputs of the natural language question. So we would iterate through each output token, and we would use again a very simple linear network to predict for each token if it is the start of the value and if it is the end of the value. Another sketch-based system is SQLova. It also uses the same sketch as SQLnet. A main difference from BERT is that it processes all the column names at the same time. So in this case, we would construct our inputs again, starting with a CLS token followed by the question, and we would mark its ending with a separating token. And then we would have its column name separated with a separating token, and we would add all the column names of the table. We would then use this, we would then give this input to BERT. We would get an output of the same length. And what SQLova does is it uses a much more complex network for these outputs, which in fact is very similar to SQLnet. It has 6 sub-networks and each one of them predicts a different part of the query sketch. And what is very interesting here is that SQLova achieves lower accuracy on WikiSQL than HydraNet. And this might be an indication that when we're using BERT or maybe language models in general, it is a good idea to follow the way that they were pre-trained when we're using them on different tasks. Now, as we said earlier, sketch-based approaches greatly reduce the possibility of errors, but there's still some possibilities to produce semantically incorrect queries. And this could happen, for example, if we have an aggregation function mismatch. So, for example, if we tried to apply the average function on a string type column, we would get a query that is not executable. So in order to tackle this, execution-guided decoding was proposed, which helps the system avoid making bad predictions that produce semantically incorrect queries at prediction time. And it does so by executing partially complete predicted queries so that the system can see that this query cannot be executed. It returns an execution error, so it's better to avoid this prediction and use another prediction. Now, moving on, let us take a look at some grammar-based systems that can generate much more complex queries and that can work efficiently on the spider dataset. IRNet is a grammar-based approach. It starts by performing schema linking on the input. So it iterates through all the words of the natural language question, and it looks for matches to a table name, a column name, or even to a value that is present in the database. So in this example, we can see that the word years was matched to a column name of the database, and IRNet marks this match by adding an additional token before the word. So it creates an input similarly to the systems we saw before by starting with a CLS token, then the natural language question with the additional schema linking tokens. And then it gives all the names of the column of the table columns and all the names of the tables of the database. And each one of them is separated using a separating token. Then it gives this input to BERT, which returns an output of equal length. And an additional step taken by IRNet is that it processes tokens that refer to the same entity in order to create a single token for each entity. So here, for example, we had the word years that also has a schema linking token. And IRNet would process these two tokens using a recurrent neural network, probably an LSTM, to create a single token for each entity. Now, in IRNet, we can use BERT, but we can also use simple word embeddings and recurrent neural networks. So BERT is just an improvement, and it is not implemented, let's say, naturally, as was done in HydraNet. So when we have this input encoding, IRNet moves on with decoding this representation into a query. So what it does, it uses a method proposed in 2017 for generating programs as abstract syntax tree, and it generates a SEMQL query as an abstract syntax tree instead of SQL. SEMQL is an intermediate representation proposed specifically for this system, and its authors argue that it is more efficient to produce SEMQL queries that can then be translated into SQL deterministically. And another very important feature of IRNet is that when predicting a column or a table name, it can make a decision to make this prediction either from the entire schema, from all the available options in the database, or it can decide to make this prediction from only table and column names that are already used in the generated query. And this is very useful if we take into account that when we're generating a having clause or an order by clause, we want to use columns that are already present in the query, and we don't need to find new columns. So this is an example of a query in SQL generated as an abstract syntax tree, which then can be deterministically translated into SQL. Moving on, RAT-SQL is another grammar-based system. The way it works is that it encodes the input as a graph, and it creates, first of all, a schema graph that contains every table and every table column. And each of these nodes are connected based on the relations of the database schema. So for example, every column will be connected with the table it belongs in. And we would also have edges that represent schema relations such as primary and foreign keys. Having this schema graph, RAT-SQL also adds nodes that represent each word of the natural language question, and it performs schema linking for each word of the natural language question, either name-based linking or value-based linking. So in this example, we can see that the word airport was matched to the table airports based on its name, and the input token JFK was matched to the table column airport code based on its value. So after it creates this input graph, it encodes each of the nodes using either GLOV and LSTM networks, or it can also use BERT, which provides much better results. But again, here we see that BERT is just an alternative for GLOV and recurrent neural networks. So having created this representation of the input, RAT-SQL uses specifically modified transformers that take into account the edges of the graph that was created earlier to perform relation-aware self-attention, which essentially biases the network towards the relations that we have discovered from schema linking and the relations that are present from the database schema. And having this encoded, this processed representation, RAT-SQL generates SQL as an abstract syntax tree. So it essentially predicts a sequence of decoder actions that, when applied, will construct an abstract syntax tree, following the exact same method that we saw earlier with IRNet.
Now let's see what are the main design choices that each of these systems have to address. Now, the first one is, of course, how the input is encoded. For example, does a system get all the information needed to solve the problem at once? And in what form this information is given so that it can be used in the best way possible? The second question is what kind of output is produced, and that essentially determines what type of queries, of SQL queries, we can understand, whether they will be syntactically correct always, whether we can avoid semantically incorrect queries. The third important design choice is concerns schema linking. Essentially, does the network have to figure this out by itself, or additional information about the schema is introduced into the system and there is more room for improvement by the network itself? Last but not least, of course, is how we represent the natural language. And essentially, as we have already discussed, the natural language is one of the main sources of challenges for the text-to-SQL task. And essentially, improving the NL representation means that we improve the performance, the effectiveness of the system. So now let's go and see how the systems can be categorized depending on the design choices they make. So essentially, we have 4 dimensions, as we already discussed. And with respect to input encoding, here we have 4 options. Essentially, we see systems like Text-to-SQL and SQLnet, where they do a separate encoding of the NL query and the schema. And then on the other end of the spectrum, you have WriteSQL that essentially encodes the whole schema graph in the input, and essentially that gives it a great benefit. Now, as far as the decoder output is concerned, we see that we have 3 options, as we already discussed: sequence, sketch-based, and grammar-based. Sequence-based has the problems of essentially introducing unnecessary complexity and potential errors in the generated SQL. On the other hand, sketch-based is an easy way to impose the syntax of the SQL output that we expect, but it has a certain degree of flexibility. And the systems like IRNet and WriteSQL that are grammar-based introduce a better flexibility in the type of queries they can understand and they can generate. Now, as far as schema linking is concerned, most of the systems, with the exception of IRNet and WriteSQL, they leave the network to figure out how schema linking should be performed. And essentially that introduces the challenge of actually being able to understand what is the correct schema mappings that should be performed. NL representation, we saw that we have 2 options: word embeddings that SQLnet and Text-to-SQL used, and then language models that all the other systems have now adopted as a preferred method. And what are the main characteristics of these systems? Text-to-SQL was one of essentially of the first neural approaches for a text-to-SQL system. On the other hand, HydraNet, for example, we see that it naturally adopted the BERT for the text-to-SQL problem. SQLova is somewhere between because it combines earlier approaches with BERT. Then IRNet introduces the new language, the new intermediate language SQL for understanding the NL query. And then we see WriteSQL with the main characteristic being that it represents the schema graph as a graph essentially in the input. And that gives it the great benefit. Actually, it's now the best system for the spider benchmark. Now, of course, there are many open challenges and research opportunities. And today we are going to touch on some of them that we think they are most important. One of them is actually overlooked, and it concerns evaluation. One of the things that are missing here is the need for a fine-grained query categorization that essentially will allow us to understand what types of queries each system can understand. For example, does HydraNet understand synonyms or spelling or queries with spelling errors and so forth? Now, a second problem and also opportunity for research has to do with the observation that on one hand, we have database approaches like the earlier systems that we saw at the beginning of the tutorial that are able to generate semantically correct SQL queries. On the other hand, we have the neural machine translation approaches that promise to be able to generalize to different types of queries and data. However, they are not there yet. Now, the opportunity here is how we can combine the best of both worlds by combining techniques, by combining components or different systems. And towards this direction, certainly we have the very nice example of WriteSQL, where we see that it combined schema linking, and it did that before actually the neural network itself. The third thing that we would like to touch here is, of course, the fact that different data sets essentially require domain-specific or even application-specific solutions. So we see solutions that are based on particular ontologies that need particular knowledge base. Essentially, we do not have universal solutions that could be transferred from one domain to the other domain. And this is a big headache, in fact. Last but not least, how do we understand the full range of queries? Some information needs may be expressed with just a few keywords, drama movies. Some others may be need to expressed in using some natural language expression. The problem is that different systems nowadays allow essentially support different queries. They cannot understand any type of queries. So how do we combine systems, or how do we come up with a system that is able to understand any type of different query? Now, essentially, the text-to-SQL problem is still a very hard problem, and for sure, it is a fertile ground for additional research. We want to thank you for your attention.